Good day, everyone. Welcome to History of Mathematics. So for today's topic is History of Mathematics in Egypt. So we're going to tackle about the ancient mathematics in Egypt. We are the Group 1 and I am J. Marcy Balendres.
Good day, I'm Romel Arnaez A. Chempo.
I am James Ray Ramoga.
So before we are going to tackle the main topic, I would like to introduce to you our objective. So at the end of the discussion, the students will be able to figure out first, number systems and computations of Egypt, Egyptian algorithm for multiplication and division, linear equation and proportional reasoning, Egyptians geometry, some Rhind mathematical papers problems such as problem 3, problem 69, problem 35, problem 26, problem 75, problem 64, and problem 50. So again, before we're going to tackle the main topic, I would like you to take back to the history of Egypt. About 450 BCE, Herodotus, the inveterate Greek traveler and narrative historian, visited Egypt. So his main point for visiting the Egypt is to know the history about the Egypt. And at that time, he viewed ancient monuments, interviewed priests, and observed the majesty of the Nile and achievements of those working along with its bank. So his main purpose as well is to know more about mathematics in the Egypt or mathematics in the ancient Egypt. And then he found out and concluded the geometry had originated in Egypt because he believed that the subject had arisen or the geometry has arisen there from the practical need for resurveying after the annual flooding of the river valley. Also, the agriculture has a very big impact to the math in Egypt. And agriculture emerged in the Nile Valley in the Egypt close to 7,000 years ago. Earliest writing concerned about accounting and primarily of various types of goods. Mathematics in Egypt was a domain especially to those trained priests, scribes, and government officials whose job is to develop and use mathematics for the benefit of the governments in such areas as tax collection, which has connection to the agriculture. Next is the measurement, the building, trade, calendar making, and as well as the rituals practices. So some of you might not know, but the Egypt has two systems of writing or two styles of writing. The first is hieroglyphic writing for monumental inscriptions. As you can see in the picture, it has like a bird and objects, so it represents more into like objects and stuff. The second style is the hieratic or cursive writing done with a brush and ink on the papyrus. So as you can see on the picture, it looks like the common one, which has other countries use as well, common writing system that other countries use as well. It was the scribe who fostered the development of the mathematical techniques. These government officials were crucial to ensuring the collection and distribution of goods. Evidences for the techniques comes from the education and daily work of the scribes, particularly in related with math. So one of the evidence that the people found out on the ancient Egypt is this mathematical papyrus. For example, is the Rhind mathematical papyrus. So Rhind mathematical papyrus is a document dating to around 1650 BC. It also found and purchased by Alexander Henry Rhind in 1858 from a Nile town in Egypt. Like what I've said, Rhind found and purchased the mathematical papyrus on the Egypt. And the Rhind mathematical papyrus contains mathematical problems that reveals important informations about how ancient Egyptians worked with multiplication, division, and as well as the fraction. So as you can see, it looks like this. So it looks like kind of blurry, but as you can see at the picture, it has like a triangles and a writing stuff We don't know about it, but it was translated by Alexander Henry, and it was found out that it was mathematical problems. The second one is the Moscow Mathematical Papyrus. So this Moscow Mathematical Papyrus is an ancient Egyptian mathematical papyrus, just like the Rhind Mathematical Papyrus, but it is also called as the Golenischev Mathematical Papyrus. This papyrus was a text and most likely written down on the 13th dynasty and based on the older materials, probably dating to the 12th dynasty of Egypt, roughly 1850 BC. Its format was divided into 25 problems with solutions by the Soviet Orientalist Vasily Vasilievich Strov in 1930. So as you can see in the picture, it's blurry as well. It looks like the same as the Rhind Mathematical Papyrus because they said that some problem in Moscow Mathematical Papyrus can be found also in the Rhind Mathematical Papyrus. So as you can see in the picture, it looks like the same but it doesn't. So now let's proceed to the number systems and computations.
Okay, let's proceed to the number systems and computations of Egyptian. So the number systems and computations in Egyptians has two different systems. First, the hieroglyphic system. The hieroglyphic system is, as you can see, there's only 7 symbols in hieroglyphic system by ones, tens, hundreds, thousands, 10,000s, and more. As it was said on the previous reporter, hieroglyphic system has combined of birds and any objects. So as you can see, the symbols of 1, 10, 100, thousands, and 10,000s, and 100,000s, and 1 million. Let's proceed to the hieratic system. Hieratic system is different in hieroglyphic system because hieratic systems has more symbols in his numbers. As you can see, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 has a different symbols. Like in a hieroglyphic system, 1 to 9 is just a 1 symbol. So let's proceed. This is the example of hieroglyphic system. So as you can see, a hieroglyphic system is more in symbols like an objects. So this is the examples, objects. Then hieratic systems. Watch carefully the different of hieroglyphic system and the hieratic system of Egyptians. Just like our writings of Egyptians, unlike the hieroglyphic system has more symbols and objects. After I show you the symbols and the differentiate of hieroglyphic and hieratic system, I show you how Egyptian algorithm solve the additions. First, 783 plus 275. This is the most important thing you to know, that Egyptian is always writing first the lowest numbers. So we write the lowest number first. So it's 3. So the symbol of 3 is this. 1, 2, and 3. So second is the 8. So the symbol of tens is this. 1, 2, 3, 4, 5, 6, 7, 8. And then the last part is 7. So hundreds. So the symbols of hundreds is this. 1, 2, 3, 4, 5, 6, and 7. Then it's the same to the other. So let's put first the ones. 1, 2, 3, 4, 5. Then seconds, the tens. Then 1, 2, 3, 4, 5, 6, 7. Then the last is hundreds. 2, 1, and 2. Then the equals of this equation, the simplest way of Egyptian is to combine all the symbols. So let's combine the symbols. 1, 2, 3, 4. Then 1, 2, 3, 4. Because 3 plus 5 is 8. Then second is the tens. 8 plus 7 is 15. So let's put symbols tens 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, then 15. The next is the hundreds. 7 plus 2 is 9. So let's put the symbols of hundreds 9 times. 1, 2, 3, 4, 5, 6, 7, 8, then 9. Then this is the simplest way of adding the symbols. But there is an another way to shortest the simplest answers of Egyptians. So, as you can see, the tens symbols is 15. So, if we plus the symbols, it's considered as a 150. So, there's a symbols of 100. Let's just convert it to 100. So, 1, 2, 3, 4, 5, 6, 7, 8. Then 15 minus 10 is 5. 1, 2, 3, 4, 5. Then our hundreds is 1, 2, 3, 4, 5, 6, 7, 8, 9. Then the other tens is we convert to the hundreds. So 100 plus 900 is 1000. So we use these symbols 1000. So these symbols. So, as you can see that the symbols of 1000, it said that 1508. So next, I want to show you and let's tackle about the Egyptian algorithm multiplication and division. Egyptian algorithm for multiplication. In this algorithm, Egyptian multiplication way is so difficult to understand. So let me show you how to multiply in Egyptian way. So the equation here gives 12 times 13. There's two columns A and B. These two columns is the way of Egyptian to solve multiplication. The first thing to do is that every time in the column A, it starts with 1. And as I understand in the books of cuts, these columns, in column A, you need to double the number. So 1 plus 1 is 2, 2 plus 2 is 4, then 4 plus 4 is 8. Then there is a sign that you need to stop doubling if the number next to the number of your doubling exceeds with 13. So 8 plus 8 is 16. So it exceeds in 13. Then in column B, the number is connected to this. Let's start with 12. And column B is also double the number. So 12 plus 12 is 24. 24 plus 24 is 48. Then 48 plus 48 is 96. Let's proceed to identify the addition of this column that might be the answer is 13. So 8. 8 plus 4 is 12. Okay. Then 12 plus 1 is 13. So should put this 13. So we get now the correct line and the correct answer 13 in this column A. In this column B, we should proceed it that we choose. So this line, and this line. Then 12 plus 48 is 60. So 60 plus 196 is 156. So as you can see, the Egyptian way in multiplication is so difficult to understand. But if you try to understand it, you will get it. So let's check if our answer in this Egyptian way multiplication is correct. So 12 times 13 is 12 times 13 is 3 times 2, 6, 3 times 1, 3, 1, 2, then 1. Then it says that 6, 5, and 156. So it's correct. So next, I show you how the Egyptian solved their division. The Egyptian algorithm in division. The Egyptian algorithm division is the inverse of the solution of the multiplication. The given equation to us is 108 divide 12. I show you how Egyptian way to solve it. So column A, then column B. As I've said that in the column A, we should start in 1 and double it. 1 plus 1, 2, 4, then 8. Then in column B is we should start in this. So we should start in 12 double it by 24, then 48, then 96. Then we should identify this. The answer of this column B should be 108. So we should identify what is the number that we should add to get this 108. 96 plus 12 is 108. 108. So in this column is that line and this line. Then we should pick this line and this line too in column A. So as we can see, 8 plus 1 is 9. So if this solution is correct, the answer of 108 divided 12 is 9. Then we should check that. 108 divided by 12 is 12. 0, 0, 108, 12 times 9 is 9 times 2, 18. 9 plus 1 is 9, then 10. So it's correct. So that's how the Egyptian algorithm for the divisions. Let's proceed to problem 3, the Rhind mathematical papyrus. The book given us equation of 6 loaves among 10 men. So the Rhind mathematical papyrus is so very hard and difficult to understand. So I want to explain it in the simplest way so you get the better explanation. So the 6 loaves among 10 men. This equation is also have a column A and column B. A, so what I've said, it always starts in 1 and double it. 1 times 1 plus 1 is 2, 2 plus 2 is 4, then 4 plus 4 is 8. And then in this column B is, first we should find the factor of this 6, 10, because in Egyptian way, in explanation, they did not exceed their numerator in 1. They're always using their numerator 1. So if your fraction is 6 over 10, we should factor it. Then the factor of this 6 tenths is 1/2 and 1/10. So the first in column B is 1/2 and 1/10. As you can see, I didn't write the 1 in the top because in the Egyptian way, this is the symbol of 1, then 1. It is a visible 1. So let's double it. 1/2 and 1/10 plus 1/2 and 1/10 is 1 and 1 over 1 and 1 over 5. Then the 1 over 5 plus 1, the plus of itself is 2 and 1/3 and 15. And the double of these numbers is 4. This means is 2/3. Then 10, 1 over 10, then 30. 1 over 30. So we are now identify the column A and column B. So we should find column A, this number 10. 8 plus 2 is 10. It's correct. We should find this in this is this number, so that we conclude that this problem 3 of the Rhind mathematical papyrus in Egyptian is valid and correct. So 1/5, 1 and 1/5 plus by 4 and 2/3 is 1/10 is 1/30 is As you can see, we should add first the whole number. 1 plus 4 is 5. So 2/3 plus 1/5 and 1/10 plus 30. So let's should be find first the denominator. So the same of the denominator is 30. 30 divide 3 is 10. 10 times 2 is 20. 30 divide 5 is 6 times 1 plus 6. So 30 divide 30 is 1. 30 divided by 10 is 3. Then 3 times 1 is 3. So 30 divided by 30 is 1. 1 plus 1. 1 times 1 is 1. So the answer is 20 plus 6 plus 3 is plus 1 is 30. So 30 over 30 is equivalent to 1. So 5 plus 1 is equals to 6. So the answer is 6. So I conclude that the Egyptian way of algorithm in the rhymed mathematical papers is correct and valid. That was the solutions of the problem 3 of rhymed mathematical papers. So next, the Egyptian mathematical letter rule dates from about 1600 BC, contains a short version of such an addition table. There are also extant several other tables for dealing with the unit, fraction, and the multiplication table for the special fraction 2 over 3. So this is the examples. 2 divided by 3, 5, and 7. So as you can see the picture, that is the example by given, and we are searching in the internet. So 2 divided by 3, 5, and 7. As you can see, the 3 and 5 is 7 is odd. So that was the example. 2 divided 3, 5, and 7. So I show you the factor of all odd denominator. This is the examples. Factor of 2/3 is factored by 1/2 plus 1/6. 2/9 is factored by 1/6 plus 1/8. So next is the problem 69 of the rhymed papers. So the last topic of my report is the problem 69 rhymed papers. Book is given us 80 divided by a fraction of 3 1/2. So the problem 69 rhymed papers, 80 divide 3 and 1/2. So there are also a column A, first column, and column B. So as I've said, column A is always starts with 1. Then the column B starts with this 3 and 1/2. 3 and 1/2. So as I've learned and by studying this problem, the first we should do is multiply the first line to 10. Multiply by 10. So 1 times 10 is 10. Then 3 and 1 over 1/2 multiplied by 10 is 35. Then the next is add itself. Then 10 plus 10 is 20. Then 35 plus 35 is 70. So this must be multiply by 10. Then this must add itself. So in this third line, we should divide it by 10. Divide it by 10. So 20 divided 10 is 2. Then 70 divided by 10 is 7. Next, thing to do is we should divide it by 3. Divide it by 3. So 2 divide 3 is 2/3. So this is the 2/3. And then the 7 divided by 3 is 2 over 1/3. Then it gives an explanation in this problem 69 that the addition of these 3 lines is a 79 1/3. So we needed to add it by 1/2 and 1/6 to this column to get this number 80. The explanation in the book is thus because 6, 3, 1/1/2 is equals to 21 and 2 times 3 and 1/2 equals 7. It follows that 1/21 times 3 1/2 equals 6 and 1/7 times 3/1/2 is equals to 2 as indicated in the 6th and 7th lines. So this we should get the 6th lines and the 7th line. So our 6th line and 7th line shows that column B and column A is 1/6 and 1/2 to multiply it by 80. In this column A shows that this pair of this 1/6 is 1/21 and the 2 is 1/7. Equals by 22 2/3 and 1/7 and over 21. To check these answers must be valid or correct, we should check it. So this is the way on how the Egyptian, the Rhind Papyrus check their answers. The answers we get in column A is 22 2/3 1/7 then 1/21. So we should double it. This number is 45 over 3 4 14 28 then 42. It shows that these numbers is divided by 2/3. So it comes up in 11 over 3 over 14 then over 42. In this column, the column A and column B is 1, starts with 1, then 1 plus 1, 2, and the 2 is divided by 2/3 is 1. So the total of this is 3 and 1/2. Then sorry that we should get the given equation in this checking. That might be 80 and 3 and 1/2. So we get now this. So it's probably correct. Then the addition of these 3 in column B, it shows that 80. So we get this number. So it shows that this Egyptian way, problem 69 in Rhind Papyrus, is correct and valid.
Hello guys, I am back and we are going to continue the topic, and this topic is linear equation and proportional reasoning on the ancient Egypt. So this topic also contains the problem 19 of the Moscow Papyrus and problem 35 of the Rhind Papyrus. In the Rhind and Moscow Papyri deal with that we today call linear equation, proportions, and geometry. So I am going to discuss to you the linear equation and the proportions only. So first, the problem 19 of the Moscow Papyrus. So this problem contains to find the number such that if it's taken to 1 and 1/2 times and then 4 is added, the sum is 10. So in the modern day, we tend to write this problem or this equation. So this problem or this equation is called the linear equation. So as you can see, it is 1 1/2 times x plus 4 is equals to 10. So in the modern day, if you're going to elaborate this equation, it will be like this. Form this mixed fraction into improper fraction, which is 3 over 2 times x, which is 3 over 2x plus 4 is equals to 10. And then transfer this 4 into the right side, which resulted to 3 over 2x is equals to 10 minus 4. 10 minus 4 is equals to 6, which resulted to 3 over 2x is equals to 6. And then divide both sides by 2 over 3. 2 over 3. If you divide this 2 over 3 divided by, multiply 3 over 2, it will going to be, the answer is 1 or x. So 6 times 2 over 3 is 4. So this is the answer for the problem 19 of the Moscow Papyrus. Actually, they didn't show the process on how to solve this kind of equation, but this problem also existed in the Moscow Papyrus. So the next problem is the problem 35 of the Rhine Papyrus. Actually, it has the same problem with the problem 19 of the Moscow Papyrus, but it looks like this. So the problem is to find the size of a scoop that requires 3 1/3 trips to fill a 1 Hecat measure. The scribe solved the equation, which would today be written as 3 1/3 times x is equals to 1. So again, this equation was also called, or is also called, a linear equation. So if you're going to elaborate this equation, it would look like the same as you elaborate the problem 19. So form this mixed fraction into improper fraction. So the improper fraction of this one is 10 over 3, which multiplied by x, which is 3x is equals to 1. So 10 over 3x is equals to 1. So again, multiply it to cancel the 10 over 3 by the reciprocal of the 10 over 3. So it would look like 3 over 10. So this one would be cancel, and then x would be 1 times 3 over 10 is 3 over 10. So the answer is x is equals to 3 over 10. But remember, ancient Egypt, or the mathematics of ancient Egypt, didn't want to use as 3, 4, 5, 6, 7, 8, and above as their numerator. So they tend to write 1 as the denominator. So to find it, or to find the 1 as the denominator for the answer, we're going to factor this 3 over 10. So we're going to find the factor that has a 1 denominator, or 1 numerator, one numerator, and then that would be the answer. So the factor of the 3 over 10 is 5 and 10. So 1/5 plus 1/10 has a result of 3 over 10. So this is the answer. It would look like this. So, as you can see, the Moscow Papyrus and the Rhine Papyrus help us to understand, or help us to know, that in the ancient Egypt, this equation or this problem occurs. The next one is the false position. The false position is a method of assuming a convenient but probably incorrect answer and then adjusting it by using proportionally. So in the problem 26 of the Rhine Papyrus, they use this false position. So the problem asks to find a quantity such that when it is added to 1/4 of itself, the result is 15. The scribe solution was to follow, assumed as 4 to be the answer. So they assumed that the 4 was the answer. So then 1 and 1/4 So 1 and 1/4 of 4 is equals to 5. And we're going to find some number that if you're going to multiply it to 5, it would result to 15. So what is the number? Any number that would fit here to find the answer 15. So it would be 3. So 5 times 3 is equals to 15. So we are going to multiply again this 3 multiply to 4. So 3 times 4 is equals to 12. So this is the come up answer for this false position. So if we're going to recheck this using our modern or the equation in the modern day, the equation would look like this. X plus 1/4 times x is equals to 15. So if you're going to elaborate this one, it would look like this. 1/4 times x is equals to 1/4 x. So x plus 1/4 x is equals to 15. X plus 1/4 x would be 5 over 4 x is equals to 15. And then multiply to the reciprocal of this one. Cancel out. So x is equals to 12. So as you can see, the answer of the equation in the modern day is the same as the answer in the ancient Egypt time. So the false position or the assumed answer for the false position that they provide is actually correct because we come up with the correct answer that is the same to the answer of the first equation. So it is correct. So the next problem is the problem 75 of the Rhind Papyrus and in the Moscow Papyrus. So the problem was asked for the number of loaves of peso 30 that can be made from the same amount of flour as 155 loaves of peso 20. So peso is the Egyptian measurement for the inverse strength of bread and can be expressed as peso, the number of loaf over the number of hectares of grain. So it would look like this, where a hectare is a dry measurement of approximately equal to 1/8 of bushel. So the problem was to solve the proportion of x over 30 equals to 115 over 20. In the modern day, it would look like this. X over 30 is equals to 155 over 20. So if we are going to derive this equation, it would look like this. So first, we're going to reduce the fraction, the 155 over 20. So the reduce of that fraction would be 31 over 4. So after we get this 31 over 4, we're going to cross multiply the x over 30 to 31 over 4. So 4 times x is equals to 4x is equals to 30 times 31 is 930. After this, we're going to divide this by 4. Divide this by 4. So x is equals to 930 cannot be divided by 4, but we can reduce to lowest term. So the answer would be 465 over 2. So again, the ancient Egypt didn't want to use 3 up as their numerator for the fraction. So they would like to find the factor of this one. So the factor of this one can be 232 1/2. So the mix form of this 465 over 2 is 232 1/2. So that would be the answer for the problem 75. So the next problem is the problem 64 of the Rhind Papyrus. If it is said to thee, divide 10 hectares of barley among 10 men, so that the difference of each man and his neighbor in hectares of barley is 1/8. So it was said that we're going to divide the 10 hectares of barley among 10 men's, in which the difference of each men's is 1/8. So in the modern day, we tend to write this equation as this. So the problem uses arithmetic sequence, and the equation would be like this: Sn is equals to n quantity 2a1 plus n minus 1 quantity d over 2. So if you're going to substitute this value, it would look like this: 10 is equals to 10 times quantity 2a1 plus 10 minus 1 quantity 1 over 8 over 2. So first, we're going to divide both sides by 10 to cancel this 10. So 10 divided 10 is equals to 1. So this will be going to 1 is equals to. So 10 divided 10 is equals to 1 again. So, and then subtract this 10 minus 1 is equals to 9 over 2. So this would the process look like after we substitute and subtract and divide. So after divide, we calculate again. 9 times 1/8 is equals to 9 over 8 quantity 2. And then after that, we're going to add this 2a1 plus 9/8. So it would look like this. So the equation would look like 16a plus 1 plus 9 over 8 over 2. So next, we're going to simplify the expression, or simplify the complex number. So like what it was said here, we're going to divide this, or we're going to make this as divide 2. So to make this division form into multiplication, we're going to reciprocal the 2. So after we reciprocal the 2, which is 1/2, we multiply it to this 16a1 plus 9 over 8. So the answer would be 1 is equals to 16a1 plus 9 is over 16. So in order to cancel this 16, we're going to multiply it by 16 both sides. So multiply by 16 both sides. So this 16 will be cancelled. So the answer would be 16 times 1 is equals to 16. 16 is equals to 16a1 plus 9. So after is collect like terms. So we're going to transfer the 16a here. So it would be negative 16a1, and then this positive 16 would be here. So 9 minus 16. 9 minus 16 is equals to negative 7. And then after that, we're going to divide the 16a1 to negative 7. So negative 16 to cancel this negative 16 here. So the answer is a1 is equals to negative 7 over 16. So the first person would receive 7 over 16. And then if you're going to add it, 7/16 plus 1/8, that would be the second one, and then second one, and then third one, the fourth one, until the 10%. So the last problem and the final problem that I'm going to tackle is the problem 23 of the Moscow Papyrus. This problem is what we often think of today as a work problem. So regarding the work of the shoemaker, if he is cutting out only, he can do 10. So if he only cut, he can do 10 cuts per day. But if he is decorating, he can do 5 pair per day. So the problem is, as for the number he can both cut and decorate in a day, what will that be? So it was asked that what is the number if he both cut and decorate per day. So in this situation, the scribe noted that the shoemaker cuts only 10 pairs of sandals in one day and decorated 10 pairs of sandals in 2 days, because he can decorate 5 sandals in one day. So 5 plus 5 is equals to 10. So therefore 10 pairs of sandals to be decorated in 2 days. So if you're going to add the 2 days for the 1 day, it would total to 3 days. So the shoemaker can cut and decorated 20 of shoes in 3 days. So to finally get the answer in the problem, the scribe then divided 10 divided by 3, which is the days, to finally find that shoemaker can cut and decorate. So 10 divided 3 is 10 cannot be divided into 3, and it can't be lowest term, but it can form into mixed fraction. So the answer would be 3 and 1/3. So this is the answer for the question, 3 and 1/3 per day. So the shoemaker can cut and decorated 3 and 1/3 per day. So next, let's proceed to our geometry.
Good day, I'm Romel Arnaez A. Chempo from BSED Math. So I am the last reporter in this group. Before we tackle, since we are done to discuss the arithmetic, linear equation, and the reasoning of Egyptian, so let's continue to the geometry of the Egypt. So geometry in Egypt is very important to know to describe the measure of the area of the rectangles, circles, triangles, and trapezoids. We have 3 problem in geometry: the problem 50 in the Rhind Papyrus, and the problem 14 in Moscow Papyrus, and the lastly is the problem 10 of Moscow Papyrus. First, we discuss Rhind Papyrus problem 50. So, example of a round field of diameter 9. What is the area? Take away 1/9 of diameter, the remainder is 8. Multiply 8 times 8, it makes 64. Therefore, the area is 64. If we derive this in the modern formula, so the modern formula is area is equal to diameter minus diameter over 9 squared. Since the diameter is 9, we change this diameter into 9. 9 over 9 is equal to 1. Area is equal to 9 minus 1, because 9 over 9 is equivalent to 1. So 9 minus 1 is equal to 8. 8 squared is equal to 64. Therefore, the area of a circle is 64. Since the Egyptian problem 50 has a same number that get in the modern formula, hence that the problem is correct. So we proceed to the problem 14 of the Moscow Papyrus. If someone says to you a truncated pyramid of 6 for the height by 4 on the base, by 2 on the top, you are to square this 4. The result is 16. You are to double 4. The result is 8. You are to square this 2. The result is 4. You are to add the 16 in the 8 and the 4. The result is 28. You are to take 1/3 of 6. The result is 2. You are to take 28 2 times. The result is 56. Behold, the volume of a truncated pyramid was 56. So if we find that correct, if we derive in the modern formula, in the modern formula, volume is equal to height over 3, open parentheses, A is equivalent to height, A squared plus height in base, plus base squared. So if we change this into number, so since the height of the truncated pyramid is 6, in the base is 4, in the top is 2, so A is represented to the height. So volume is equal to 6 over 3, open parentheses, 2 squared plus A and base plus base squared, close parentheses. So V 6 over 3 is equal to 1. If we are going to lowest term, so 2 squared is equal to 4, plus 2 times 4 is equal to 8, plus 4 squared is equal to 16. So if we are going to add this in the parentheses, the result is 28. So if we times that 2 times 28, the result is 56. Therefore, the problem 14 of Egypt is correct to derive in the formula in the modern day. We are going to discuss the last problem of geometry. Lastly, we are discuss the problem 10 of the Moscow papers. So, we are need to determine the surface area of a hemisphere. Dimension that the basket has amount of 4 and 1/2. Take 9 since the basket is half of an egg, result is 1. Take the remainder 8. Take the 9 over 9 of 8. The result is 2/3 plus 1/6 plus 1 over 18. After subtracting the result of 2/3 plus 1/6 plus 1 over 18, the result is 7 1 over 9. We are going to times into the mouth of a basket since we preserve the 4 in 1/2 to get the surface area of a hemisphere. So we are going to times the 4 in 1/2. The result is 32. Therefore, the problem 10 of the Moscow papyrus of Egypt was correct if we derive in the formula of a modern day. And that's all. We are going to end this discussion. Thank you.
So therefore, to conclude, all in all, mathematics in the Egypt or in the ancient Egypt was in the domain of specially trained priests and scribes, government officials whose job is to develop and use mathematics for the benefit of the government in such areas as tax collections, measurements, building, trade, calendar making, and ritual practices. Mathematics was a tool of power, and its method were passed on only to privileged few, often through an oral tradition. Hence, the written records are generally sparse and seldom provided much detail. Again, this is Group 1, and thank you for watching.